So, welcome to lecture 21. We're going to talk about MOS biasing this time, plus some small signal analysis. As usual, just a few announcements. Your homework 7 is online and due this coming Friday. The lab number 3 pre-lab was already due, so I guess I don't even need to have that in this. Should have already turned that in. But the lab number 3 experimental part is due next week. In lab section, and the lab number 4 pre-lab is online, and that's going to be due the week of October 26th, which is the week after next. You're not going to do the experimental part of that lab, but you will do the pre-lab, and so it's really going to end up being like a homework, I suppose, in biasing. And so I guess to get, let's see, can we get an extension for lab 3 since many of us have only finished part 1 in the lab section? Is that right? Is Kieran here? Yeah, Kieran is here. Kieran, what do you think? And Tu-Cuong.
Yeah, that tracks kind of with what I saw this week in lab is some people maybe just started part 2, but most people were on part 1. Yeah.
I see. So they're not really finished with the experimental part. I know there were some people who were having some issues with their 82 as well. And so probably just because of those issues, tell you what, we will discuss more and we will announce on Piazza for this. But probably hearing Kieran. I want to hear from Tu-Cuong too, but let's do that offline right after class. Any other questions? I'm thinking yes, we'll do it, but I just want to know the extent to which there were people having problems with their 82s and the equipment and that. Let's see. Okay, so not hearing anything else. Today we're doing discrete MOS biasing, then small signal analysis. If we can get to it, what I'm going to do is more MOS biasing than I've done in the past, because I've seen in the past that students have some difficulty with it since it's a bit different than the bipolar biasing. And so let's get to that. So last time, this is what we ended up with. We ended up with these sort of guidelines, not rules, but guidelines, starting points for what you want to do when you bias up a bipolar circuit. I'm not going to show the bipolar circuit. I'm just going to show that we were able to come up with 1, 2, 3, 4, some rules for this. Then we started looking at MOS biasing. And in this case, we can use a similar strategy for discrete MOS circuits as with discrete bipolar circuits. The difference, however, being that we can't just assume that VGS on is a constant like we assume VBE on for a bipolar transistor was a constant. So rather, we have to determine VGS. And we even have to iterate in order to get the right VGS because the threshold voltage depends on some other voltages. And so why is it that for bipolar we can just assume some VBE on of 0.7 volts and for MOS we can't really do that with enough accuracy? Sometimes we can do that if we don't care that much about accuracy, but a lot of times we can't. The reason is that for MOS the current goes as VGS minus VTN squared, whereas for bipolar it went with e to the VBE power. And so if you look at bipolar here, and you have, you plot collector current versus VBE, that shoots up very fast. And it almost looks like that you have infinite current happening at a very specific VBE. And that specific VBE, as we've said already in the past, happens to be on the order of 0.7 volts. Right. It'll vary around there as the currents vary, but it's right around that 0.7 volts. For MOS, you don't have the same situation because the curve doesn't go up as fast. It goes up by a square law of the voltage. And so I could have some current IDS prime and some other current IDS double prime, and they're different currents and they require different VGSs. There's a significant difference between the VGSs that these two currents require. And so because of this, I can't just say VGS is some voltage here. I actually have to calculate what VGS is. And so with that as a backdrop, let's go ahead and do a problem then, do an example. And this is what I haven't done in the past, an example. But let's do an example this time to let you see what you need to do for MOS analysis. And so I'm going to take a circuit a lot like the circuit that we had for bipolar. So I just took I took the bipolar device from our previous circuit and just replaced it with an MOS device. And instead of calling this RC for R collector and RE for R emitter, this is RD for R drain, this is RS for R source. I have a similar voltage divider out here to set some voltage at the gate, VGG. And I'm going to worry about my current ID. I've been calling it IDS, but I'm just going to call it ID here as the current going to the drain, because you know that the current going to the drain is the same as the current going out of the source. It's just going to go straight through here. It's not going to go into the gate. And also the gate current, as you should already know, is 0 for an MOS transistor. Okay, and so for this MOS transistor, So I could specify a circuit and then say get the DC operating point, but instead, just to show you some design, let's go ahead and design this. Let's say that we want to design for a certain drain current. So for this example, let's design for a drain current of 100 microamps. And that's typically what you're going to see that you're going to want to do for these designs. You're generally designing to get a certain drain current, and you're doing that because that certain drain current will actually determine basically all the properties of the amplifier if you're making an amplifier. So you care about ID because ID determines the amplifier specs. As we'll soon see. Okay, so there's my spec for the problem. So how do I go about doing this problem? Well, naturally you want to do things like apply KVL and that sort of thing, Kirchhoff's laws, to analyze the circuit. And this really just boils down to circuit analysis at this point. And so let's start doing that here. Let's first do things that are very quick. So that I have no current going to this gate. So this really truly is a voltage divider with an open circuit at the output. So I can immediately write that this voltage VGG, that's just going to be equal to this R2. Well, that's going to be equal to the VDD times R2 over R1 plus R2. Okay, I've already said that IG is equal to 0. And that basically means that my gate voltage is going to be equal to VGG. Okay, very obvious thing right there. And so now what I'm going to do is I'm just going to use Kirchhoff's voltage law and take a look at that loop there. And around that loop, just apply KVL. And so if I do that, then VGG is going to be equal to basically VGS plus the voltage drop across RS here, which is going to be ID times RS. Okay, and so I can rearrange this here to get an expression then for VGS, which is going to be VGG minus ID times RS. Okay, and so with this, I did a bit of Kirchhoff's laws here, and I actually didn't really have to do a lot of this for the design problem, but I did it mainly because I need this for the operating point determination problem that I'll do later on. But for the design problem, I guess what I'll do is I'll just start writing equations that dictate this current, ID, flowing through that transistor. So we know what that current is flowing through that transistor. We know that, and let me switch to a different color here while I do that. So let's just write the equation for the drain current. Let me get back to that size. And so I know that the drain current for an MOS transistor, that's just 1/2 mu n times Cox times W over L times whatever the VGS is minus whatever the threshold voltage is squared. And then there's this 1 plus lambda times VDS with that as well. And so I have a bunch of parameters there, and I guess for this problem I need to define those parameters. So let's define some of those parameters here. Let me go back up here and write down some parameters that we can use for this. So let's just say that the VT naught for the threshold voltage is 0.7 volts. That's the threshold voltage when VSB equals 0, as we talked about before. Let's say that gamma is a typical 0.5 volts to the minus 1 is what that is. Let's say that, that should be volts to the 1/2, not minus 1. Okay, let's say that W over L for this transistor is 20 to 1. So usually you write that in microns. So that's 20 microns over 1 micron. So let me do it like that. And then finally I need the strength of my transistor. So let's say that the mu n Cox for this, and this is how you're usually going to see it spec'd, is going to be 120 microamps per volt squared. And so again, this is what we want to do. We want to design for this ID. And I've got things bunched together. That's all right. We'll leave that bunched together. Maybe I'll put a line there, like that. Okay, so these are our goals right here for this design. Let me switch back to blue now. And continue this. And so usually when we're doing these biasing problems, because lambda is pretty small, I'm not going to be too concerned about lambda, so this part I'm just going to neglect. Since lambda is a small number there. That's going to be like 0.01, 0.02, something like that. And so now I'm left with just this part of the equation there. And so with that part of the equation, what I want to do is sort of get an expression for that VGS. And if I go ahead and do the algebra here, I find that VGS is going to be equal to whatever the threshold voltage is plus the square root of 2 times whatever ID is divided by mu n Cox times W over L. Okay, so that ends up being my VGS voltage. And if you look at this, this part here is basically the amount of voltage beyond which we create that inversion layer in the MOS transistor. So all we need to create the inversion layer in the MOS transistor is VTN. Okay? But usually we have a little more voltage there to get a certain amount of current, which is going to be dictated by this equation here. So this part here is often called VOV, which people term the overdrive voltage. You're going to see that terminology. And the reason why is because that's the extra voltage that you're putting on. You don't need to put that much voltage there, but that's the extra voltage you need to not only get that channel, but to also get a certain current flowing through that transistor, since you see ID is in this equation right here. Okay, so again, I want ID is equal to 100. And so now I'm just going to plug in numbers into this equation. All right, so let's go blue. So for ID equal to 100 microamperes, I can calculate now my value for VGS. That's just going to be equal to the VTN value, which is 0.7 volts, plus the square root of all that stuff, square root of 2 times the current that I want to have flowing through there. That's ID, that's 100 microamperes, divided by 120. Or see, the units of this were in microamperes per volt squared, the mu n Cox there. Divided by my W over L ratio, which is 20. I guess I should show it. I mean, that square root's meant to go through that whole thing there. Okay, if you go in and plug in your numbers, you're going to end up with 0.7 plus 0.29, and so end up with 0.99 volts, which for all intents and purposes is 1 volt. but I'll just say it's 0.99. If I were doing this for real, I would just say it's 1 volt and just proceed with that. Just make that approximation. Okay, and so from here, I now have that voltage drop VGS there, which means now I can determine the current ID, which is also flowing through RS. Right, so the current ID going to the drain is the same as the current going through RS. And so that now allows me to determine RS. So I can write my equation for ID is equal to IS is equal to the voltage drop across RS, which is going to be VGG. I want that to look like G's. Minus my VGS minus VSS, which is my lower rail voltage, divided by RS. Of course, what I really want to find in this is RS. Design means I want to pick RS in this case. Okay, so to pick RS, I just need the same equation, that VGG minus VGS minus VSS divided now by the ID that I'm going for. Okay, now I need to know VGG, and so I'm just going to use that rule that I want. So if I want to drop 1/3 of the voltage, right, so for 1/3 of my supply voltage, VDD minus VSS, dropped across the input, what's effectively the input. And so I'd say the input is like this here. Whoops. Okay. That's what I'm calling my input, sort of, that much there, from there to the VSS. And let's give some VDDs and VSS here. And so let's choose plus and minus 10 volts, or plus and minus 5 volts. Plus 5 volts. Make that minus 5 volts there. And so for this, if I choose these values here, if I want to drop that across the input, then I'm going to want to choose R1. Say we could choose R1 to be equal to 100 kilo ohms, R2 equal to 10 or 50 kilo ohms. Right, because if I choose those, then that means VGG, which is that voltage divider, that becomes 50 kilo ohms divided by 150 kilo ohms, which is 1/3, right, times that total voltage here, VGG minus VDD minus VDS, okay, then plus the VSS there, and you're going to see that that's going to be equal to what, minus 1.7 volts. Okay, so that establishes VGG as being equal to minus 1.7 volts there. And so now I can plug that into this equation up there for RS. Go to the other side here. So now I can finally get RS. Go back to blue. And plugging those values in, that's minus 1.7 volts. Minus my VGS, which I calculated to be 0.99 volts, minus my VSS, which was minus 5 volts, divided by the current that I want, 100 microamperes, and that then ends up being 23.1 kilo ohms. So that's kind of a design, right? My design includes R1 and R2. So I could settle on this design right now. I could say my design is this and that. Now, that I could say is my total design. However, because this is MOS, it might not be actually accurate. So if you look at my original circuit, I have a voltage Vs right here, but the bulk of this thing, you could see, is actually tied, ooh, too thick. The bulk is actually tied to this VSS. Okay, so my VSB is actually equal to the voltage dropped across my RS right now. And that's going to actually affect my threshold voltage. So I have to be careful with that right now. So let's write down what our VSB is. The voltage between the source and the bulk. So that is equal to this VGG minus VGS minus VSS. And so that's the same thing as the thing up top here. And that thing up top was 2.31 volts. Okay, so I have a VSB of 2.31 volts. But remember, the voltage that I use for VGS, this VTN right here, I'm on the right side, this is a function. Let me switch to another color here because I'm about to go into another iteration. Whoa. I was using very thick pen in office hours, so I have to change this thickness. Okay, so this VTN, that's a function of VSB. Remember? And so that specific function of VSB was VTN. Let me go green again here. Is equal to the threshold voltage at 0 VSB, which is what I started with, right? So the assumption that I made here in putting this in here was 0 volts. That VSB was 0 volts. Okay, I'm going to assume that to start, but I need to check this later. And I've already checked it. It's not 0 volts. I just said it's 2.31 volts. Okay, so now I have to use my equation for threshold voltage, which we saw in a previous lecture. Threshold voltage VTN is equal to VT naught plus gamma times the square root, there's where VSB is, plus that 2 phi f that we had before, minus square root of that 2 phi f that we had before. Now I have to plug these numbers in. And so if I plug all these numbers in, I get VT naught, still 0.7 volts. Gamma I gave as 0.5. That has to be multiplied by square root of 2.31 plus 2 phi f. Did I give that? I didn't. That's generally 0.6 volts. So let me stick that up here. It depends on doping concentration, but that's what it ends up being. We talked about that in our physics part of the class. But going back here, so I already wrote that 0.6 volts. And so minus 2 phi f on its own, square root of 2 phi f on its own, that's also 0.6 volts there. And this then ends up being equal to 1.16 volts. That's different from the original 0.7 volts that I assumed. Okay, since that's different, I want to do an iteration. Okay, so this is already part of my iteration here, but I can call this my first iteration. And on that first iteration, what am I going to do? I'm going to calculate VGS again. So I'm going to go back to that voltage that I had in the beginning and actually calculate my VGS. So this expression here that I used to get a VGS of 0.99 volts, I'm going to plug in new values for this. Now VGS is going to be that 1.16 volts that I just calculated, plus still that 0.29 volts that I had, or 1.45 volts. And with that new VGS, what that tells me is that my new RS is going to be minus 1.7 volts minus this new VGS, 1.45 volts minus 5 again, divided by the current that I want, which is 100 microamperes. This ends up being 33 kiloohms. And so you see my first answer, when I just made an assumption for this threshold voltage, remember what that was. I guess it's up here. Its RS is 23.1 kiloohms. Okay, but by doing this iteration, I now have a better value of what that RS has to be. And I can continue to do that iteration beyond this, right? So here I can determine, I can continue sort of in one more iteration, and I'm not going to do this whole iteration, but from this, I can also get a new value for VSB. So the new value for VSB in this case is going to end up being the same voltage as this up here, that part up here, and if you evaluate that, that becomes 3.3 volts. And if you go ahead and use that, then you get a VTN equal to 1.3 volts. And you can go to yet another iteration. You can go to a second iteration on this. And that will give a more accurate. I'm getting lazy here. More accurate value for RS. And RS is what we're trying to design here. This is already a more accurate value of RS than the previous one. But if I continue to iterate, I'm going to get an even more accurate value. So in this, basically, I could keep going until RS converges. To satisfaction. Obviously, you can go forever with this. It'll keep converging, but at some point you're going to be satisfied. And for me, I'll probably be satisfied with this 33 kilo ohms. I won't have exactly 100 microamperes, but I'll have something close enough to get my amplifier to work the way that it needs to. And you will learn, we haven't learned that yet, but you're going to learn that in a bit, what you need to get your amplifier to work like. So what I did was I just showed you the design procedure. The way to design with this kind of biasing to get a certain amount of current there. And I think I'm just going to grab something that I wrote up before the lecture. That just gives you that design procedure, exactly what I just did here. And I'm just going to plop it right in to that point there. I didn't quite get the whole thing. Let's try again. I think it's because I was trying to avoid that other stuff, but no, I still didn't get the design procedure. Oh, that's why. I'll erase this. Okay, so this basically summarizes what I just did. I won't go through this here because we just did it. So you can read this on your own here. But that's what the design procedure ends up being. It was tedious. Right? You saw what I was doing. This was pretty tedious. And so it's not a fun thing to do. It's tedious because this is a nonlinear problem. Right? We had to do that iteration because there were dependencies on different voltages that showed up several times in the same equation. If I had to write a closed form equation, you'd see several dependencies there. Okay, that was not fun. And that's part of the reason why I did that, to show you that this is not fun. Okay, if we want to solve nonlinear problems, there must be a better way to do this. And so I'll say you cannot avoid this, what we just did. So what we just did is not a waste of time, at least to get the DC operating point. But when we talk about amplifier performance, we're going to be able to avoid it through something called small signal analysis. And if there's anything in this class that you take away as important, I would say the most important thing you take away from this class is small signal analysis, which we're about to go into. But before going into that, let me just say that this was design. Analysis is even worse. Okay, so the procedure to analyze this, or say I gave you all the resistors and I gave you the transistors with all that, and I wanted you to determine the drain current for me. Well, if I asked you to do that, then the procedure you'd have to follow is this, which I'll just grab from here as well. is just that. Let me grab something else here because I'm going to use it. So this is the design procedure to find the DC operating point. You start with that IDS equation. You know that the threshold voltage depends on this equation here. You determine VGS. You determine VS, so you get VSB. You iterate, right, to get a new value of threshold voltage. You plug that in and get a new value of VGS. And now you iterate to convergence. But because this, the reason why I'm saying this is worse is because you have to solve this equation here. This equation is it's a quadratic equation, right? So you have to use the quadratic formula or something like that to solve this equation. That's not fun. So that's really a nonlinear type equation. Yeah, okay, so Kieran is answering that question correct. Why do we assume saturation? It's because we want to maximize the drain current. It's basically that's the area where you're able to get gain out of the transistors. You won't know that until we go through small signal analysis and a little bit more. That's coming. You'll understand that very soon. And so, yeah, there's iteration going on. It's tedious, but it's effective for discrete off-chip MOS circuits. I should say now that on-chip, we don't do this much stuff. We're not using resistors like this on-chip. We're actually using what's called current mirrors. And so let's talk about that just a bit. I went through this very quickly because, you know, it's a lot of the same procedure we talked about, but worse. And so you can actually, you know, read through that yourself. But let's talk about current mirrors for a bit here, because that's the way MOS really is biased on chip, and bipolar as well, I should say. And so what do I mean by current mirror? So just to start off, so what I just said, for discrete off-chip circuits, avoid transistors. That's what we're doing right now, because in this class you're learning to design discrete circuits. Discrete means at the board level. So the reason why you want to avoid transistors is because discrete transistors are more expensive than discrete resistors. Okay? Once you go integrated, you go on-chip, you want to avoid resistors. It's the exact opposite. Resistors take up more space than transistors when you have an integrated circuit process, and so they cost more money, because space is money on an integrated circuit chip. And so when you integrate, you want to use lots of transistors and few, if any, resistors. And that then dictates the way that you want to bias. And so just to give an MOS example, it's the same for bipolar. On chip, you want to bias by what's called current mirrors. Okay, so let me draw an example of a current mirror biasing. So say I have an amplifier out here. Well, say I've got a couple amplifiers out here. You don't know what an amplifier looks like yet, but I'm just going to tell you, and you know already, they involve transistors. So this will be my amplifier. Maybe this will be my input voltage, and that's what I want to be my output voltage from this amplifier. And the amplifier, of course, needs power, so I'm going to show a supply rail there. Okay, and say I've got another amplifier out here. Say right here. It's going to have the same supply rail. So all of these are going to VSS, bottom supply rail. And it's the same kind of thing. I'll call this VI2. And that'll be VOut2. VI1, VOut2. These are just two different amplifiers. Okay, and that's what we're going to do for amplifiers. We use transistors to amplify. But we have to bias these things up, meaning we have to give them a current, just like we did with that resistor circuit. On chip, you don't use that big resistor circuit. On chip, you use one resistor. You still need to use a resistor because the way we generate currents, as you've seen with biasing bipolar or MOS, the way we generate currents is basically put a voltage across a resistor, and that then creates the current. It's generally always the case. So anytime you want to figure out what the bias point of a circuit is, look for a resistor. Okay, and find a voltage across that resistor. Then you can find the current, and that's going to pretty much determine the rest of the bias point. On chip, the way that we generate that current, though, is different. We use the complementary device. This was an NMOS device. These two amplifiers are based on NMOS devices, but notice I'm using a PMOS device up here, my complementary PMOS device. And I'm going to hook this up like this, which is kind of a diode connection. You've seen a little bit of that maybe in some of your homeworks. And then I'm going to take one resistor and I'm going to call it R bias. This is the only resistor on the whole chip. Okay, so this is just one resistor. That's the only resistor on the chip. It's going to take a lot of space. Okay, but the important thing is that if this is my transistor, which I'll call M1, so for MOS transistors, I'll call it M1. And if I size M1 to be W over L1, then what's going to happen is I'm going to drop a voltage across this, and that voltage dropped across this is going to be the VGS of device 1. Since it's PMOS, I usually make that absolute value. That's VSG of device 1. Okay, I'm dropping that voltage across this, according to my plus and minus that I'm showing there. And so across this resistor, I'm going to have a voltage there, and I have VSS there, which means that my current, I bias, is going to just be equal to the voltage difference. It's going to be VDD minus VGS1 minus VSS divided by that bias resistor. So see, I'm generating that current exactly the same way that I did in that other circuit. But I'm now doing it with this transistor where I've tied its gate and its drain together to create a very specific voltage. The voltage here, VSG1, is the same as the voltage drop between the source and drain. So that's when I'm making this, and you'll see that's behaving like a diode. Now I've generated a voltage here. And the voltage right here gives me the exact voltage I need to generate this current. And so if I go back over here to complete this amplifier, and I give this amplifier, instead of a resistive load, a load that is a transistor, which I'll call M2, which has exactly the same W over L as the transistor on the left, and I then attach this to that gate, this is now going to give me exactly the same current. That ID, which then runs through this transistor down here, which I'll call M3, that ID has to be equal to I bias. Because the voltage VSG2 for M2 has to be equal to VSG1. So it's basically these transistors. This is a replica. You could say that this transistor out here is a replica of that transistor. It's got the same VGS, it's got the same W over L, so because of that it's got the same current flowing through it. Okay? And so that's how I establish this ID is equal to I bias for this transistor here. I do have to solve a nonlinear equation, but just once. And once I get that, I have this voltage, I just distribute it to all the different amplifiers on this. So if I wanted to bias this amplifier that I have at the bottom, shift that a bit. Then all I would do is also load this with a similar PMOS device, have that at VDD. This device also has to have a W over L equal to the W over L of device 1 or 2. They're the same. And then I'm just going to take this voltage here and attach it to that. And when I do that now, this current will also be equal to I bias. So I'm basically distributing that voltage to give all of these two different amplifiers a bias point. And the bias point, again, to me, means giving it a certain current. Okay? And so that is where I think I'll stop talking about bias points now. And let's now start to at least start our discussion of small signal analysis. Again, one of the most important discussions we're going to have, one of the most important topics that you will have in this class that will be very general. It won't be just for transistors, it'll be for all sorts of things that you may encounter later on as you're doing different types of designs. So for this to start out, I've got some things already written up, so I'm going to go ahead and use those. So let's talk about this small signal analysis. Well, before that, let me stop and say, any questions about MOS biasing? The stuff that I did, even current mirrors, that sort? Anyone? Can use the chat? Okay, I don't see anything else there. And so let's talk about small signal analysis. So small signal analysis is kind of the solution to what we just went through. We just went through a lot of tedious labor to solve a nonlinear problem. And transistors are nonlinear. So when we put signals through them, time varying signals, to do it right, you're going to have to solve a nonlinear problem, really. Unless you know how to do small signal analysis. So let's talk about this. The small signal analysis is a method to solve nonlinear problems by linearizing them around a specific coordinate point. And so what do I mean by that? So we talked about linear and nonlinear resistors before. So in our linear resistor, straight line in the IV characteristic, I equals V over R. Our nonlinear resistor, different symbol here, and it can now look like a curve in the IV plane. And so I have to say that I is equal to some function of V, and this could be some nonlinear function. And so as we've seen, transistors are nonlinear devices, right? I for a transistor is some function of voltage, and it's not a linear function. We see that for both MOS and for bipolar. We've already experienced difficulty solving for DC operating points for nonlinear transistors. We just did that. So solving circuits with more complex inputs, like sinusoids or sums of them, right? Logically, that's going to be even more difficult, right? If we took that much time solving for just one voltage at one time, just think if we start varying that voltage over time, now we have to solve all those problems. That can take a very long time. Okay, so we need some way to simplify these problems, and that's what small signal analysis is. So let me describe, not using transistors, but using a very general sense, exactly what we're doing when we do small signal analysis. And yeah, let me use this example here. So let's take the example of a two-terminal nonlinear circuit. So our transistors, they're three-terminal, so they're even going to be more complicated than what I'm showing here. But let me compare and contrast what you already know, which is this above, to what you're about to learn, which is this down here. So what you already know is that if I take a voltage source VB and have a source resistance RB, and I shove that across some load, in this case I'm just taking a linear resistor, I can write some equations for this circuit. So the first equation I can write, if this voltage across here is VQ, then VQ is equal to VB plus the voltage across this resistor, and if the current is in this direction as I'm showing, that means it's going up through RB, right? And so that means the voltage drop is going to be minus IQ times RB. So VQ is VB minus IQ times RB. On the other side, I can write a simple equation. VQ is just going to be this IQ through RL. Right? These are two linear equations. We can solve the simultaneous linear equations. That's where, a lot of your linear algebra comes in there. And this one you already know the answer. It's VQ is going to be RL over RL plus RB times VB. It's a voltage divider is all it is. Okay, now let's substitute for this resistor for a nonlinear resistor. Maybe this one here that has that transfer function right there. And so if I do that, what happens? I could still write this first equation. That's still a linear resistor, so I could still say VQ is VB minus IQ times RB. Okay, but for this right here, for IQ, which is a function of V, that's now going to be a function of the voltage across it, which is VQ. This is a nonlinear equation. And so I have to solve these two simultaneous equations, and when I do that, this is what I get. I get VQ is equal to VB minus the F of VQ times RB. That means I got VQ on both sides here. And this VQ is going to be in some horrendous nonlinear thing. Maybe it's in some square root or it's to the third power or some exponential or something. Just an example, if I is equal to F of V, that could be 2 times V squared plus V cubed. And this equation here looks like this. VQ is VB minus all this with the square and third power times RB. That's not easy to solve, as this is saying right here. Okay, we need an easier way to do this. And so how can we make our job a little easier? Well, before talking about that, let me just define a couple things, because we're going to need to define a couple things to to make our life easier here. So let me define some notation. And so this is going to be our nomenclature for the rest of this class. This is going to be the nomenclature that you use if you take 140 and 142 and all the circuits classes here. And so that's why in some parts of the earlier lectures I was being particular about whether I used an uppercase or a lowercase variable or subscript. And so if this is my total signal, usually this is what our signals will look like. This is what they'll look like in the time domain. If this is voltage, the total voltage VB, which is that, then usually as a function of time, that total voltage VB consists of some constant component, V capital B, plus some small signal AC component. So some time varying component there. We all know already that any time varying signal I can pretty much represent as a sum of sinusoids. And so we'll just take a sinusoid in this case, because if we can solve it for sinusoids, we can solve it for any general signal. And so that's what this is showing. This is showing that this total signal is a DC component, V capital B. That's what I'll call the large signal DC component, plus an AC small signal component, little v, little b. Okay? Lowercase v, lowercase b. I'm being very particular about what case I'm using. And at the bottom of this says exactly what we're doing here. So if total signal is V, little v, capital B, then that's equal to the DC component, capital B, capital V, capital B, plus the small signal component, little v, little b. And so for DC components, we will use an uppercase variable and an uppercase subscript. For small signal components, time-varying small signal, we'll use a lowercase variable and a lowercase subscript. And then the total signal, different books do different things. Okay, if you pick up one textbook, they may use a lowercase variable and an uppercase subscript. Use another textbook, they may use an uppercase variable and a lowercase subscript. Okay, but the thing to remember here, if the variable and the subscript have different cases, the opposite cases, then that's the total signal. Okay, I'm in this class using little v, big B, because that's what Sedra and Smith does. But when you take 140, if they use Gray and Meyer as your text, they're going to do the exact opposite. Okay, so just remember that a different case variable and subscript, that means the total signal. Okay, and so now let's proceed to actually at least start our nonlinear problem. Armed with this notation here, let's at least start attacking our nonlinear problem. And so here, using this notation, I can now take the circuit that we just looked at and sort of break it down into those components. So I'm going to have that resistor still RB. And instead of just drawing a VB, a little v, big V, I'm going to split it up into its little v, little b, and its DC components, it's a large DC component, big V, big B. Okay? And this now is going to be put across my nonlinear resistor. So this part of the circuit is the same as what we showed before. So there's my nonlinear resistor. It's described by current is equal to some function of the voltage across it. And I'm going to have my ground still here. And this voltage drop across here is going to be, okay, that kind of shows me the folly of what I just did. Let's see if I can grab parts of this here. I can, it looks like. I need more space, basically, is what. I'll fix that later on. But between the plus and minus here, this voltage I can now write as V capital Q plus little v lowercase q. Okay, so that's what I'm trying to get at here. That this is now, it's the same circuit. All I've done was just split the input voltage into its components now. And so with this circuit, I can now write a couple things. Also, this current flowing through this thing, I'm going to split it into components. This is going to be a capital I capital Q for a large DC component, plus a lowercase I lowercase q for the AC component of that. And so for this whole circuit, I'm going to be able to write this total voltage VQ plus little vq. That's going to be equal to, if I just look at the left side, VB, or capital V capital B, plus lowercase v lowercase b, and minus the current flowing through the RB, which is a function of the voltage across this device, this nonlinear device. So that's going to be a function of capital VQ lowercase vq times that resistor RB. So that now becomes the equation that is governing the performance of this circuit. Now, we haven't solved anything yet because this thing is still nonlinear, right? So we still need to solve this thing, which is nonlinear, but now that we've split this into large components and small components, we can now take advantage of Taylor series. So we can now use a Taylor series approximation for this function. And then if we keep voltages small, which is the idea behind this little VQ, we can now linearize the whole thing. And so let me write this. For this, we can use a Taylor series approximation for f of v around a bias point V is equal to capital VQ. Okay, so this is Taylor series. You may remember that from your math classes, but I don't require that you remember that because I'm going to tell you what a Taylor series is, basically. So let's just review what you should have learned in your math classes. I guess calculus, at the very least, you'll learn Taylor series. So if we review Taylor series, any function, I'll call it f of x, use x instead of voltage here to be general here, can be approximated for points near x is equal to A. So A is like my bias point. Let me make that look clearer. By, and this is just the standard definition of a Taylor series, f of x is equal to f of A plus f prime of A times x minus A. Hopefully this is jogging your memory of this. Where f prime of A is the first derivative. Of f with respect to, in this case, x, evaluated at x is equal to A. Okay, and I can keep going here. It has more terms, plus f double prime evaluated at A divided by 2 factorial times x minus A squared plus, I could do dot, dot, dot. I can expand this n times there. F to the nth derivative of f with respect to x over n factorial times x minus A to the nth, and so on and so forth. You can get an infinite number of these things. Okay, so hopefully this is jogging your memory. And as I write this, the natural thought is, well, wait a minute, this is not really making things easier. That's a pretty gnarly looking equation. However, what we're going to do is we're going to say that we can approximate this whole thing by just f of a plus just that first term, f prime of a times x minus a, for cases where x minus a is small. Okay, and so in writing that, what I'm doing is sort of separating out a large signal problem from a small signal problem. So this is what I'm going to leave you with today, but I'm going to write it down. Okay, first thing to notice here is this whole equation here, which I'm now using to solve my whole problem, this is linear. Okay, which means it's easy to solve. That's basically a linear equation that's easier to solve. At least part of it is linear, I suppose. The way you should interpret this, the x here is the total signal. The A is my bias point. And so in my circuit, that's what I'm calling my DC bias point, which means if I take the total signal minus my bias point, what am I left with? I'm left with my small signal. So that x minus a is my small signal. And so then when I go back to this equation up here at the very top, and this is the last thing that I'll do here, I could take that equation and using this Taylor series expansion that I'm talking about, rewrite that equation as VQ, capital VQ, plus little v, little q, is equal to capital V, capital B, plus little v, little b. But now I'm going to separate this out into what I have in my Taylor series expansion. This is now going to be the function of VQ, that times RB, minus, minus f prime, the first derivative, evaluated at that operating point VQ, times VQ, times RB. And so this whole equation here, right, this XA, let me use a different color here, that XA part of that corresponds to my VQ. That is my small signal. And you notice that I've separated out that small signal from the capital VQ in this term over here. Okay, so I've set the whole thing up now, and what this really is now is two problems in one. This is like two problems superimposed. It's like a large signal DC problem, which we're going to have to solve just like we just solved that MOS biasing problem. But it also includes, with the little VQ, the little VP, and the little VQ there, a small signal problem that actually governs all of the amplifier characteristics in the end. And you can see that's a linear problem. You may not be able to see it yet, but in the next lecture, I'm going to separate these two into two problems. And determining the amplifier performance is going to be basically solving linear equations. Okay, so with that, I'm going to end up, and I will see you on Friday for the rest of this.